Welcome to this tutorial on MPLAB. In this video, we'll cover how to download, install, and use the MPLAB development environment, along with the PIC-AS assembler. This is essential for practicing the examples from the handbook and labs on your home computer. MPLAB is the primary development environment for microchip PIC microcontrollers, specifically the PIC-18F8722, which we'll be using in our exercises. The software is free and compatible with Windows, Mac, and Linux. To download it, search MPLAB on Google and go to the microchip.com link. Download the version that's suitable for your operating system. For this guide, we'll be using Windows, but the process should be similar for Mac and Linux. We're also going to need the PIC-AS assembler, which comes as part of the XC8 compiler suite. Simply search XC8 on Google, and you'll find a link to the download for your specific operating system on the Microchip website. Here you can see I'm downloading the Windows version. The install process for MPLAB is relatively straightforward. Simply click Next and accept the license agreement. Then you need to make sure that your C drive is where the package is installed on. We sometimes find these issues if students have international characters or perhaps they use the X drive for their installs. You might also want to uncheck the privacy notices. On this page here, we're only going to be using the 8-bit PIC, so you can uncheck the other options so you don't end up downloading gigabytes worth of files. And that's it. Press Next. Midway through the install process, you'll get asked whether you want to install some drivers. These are for the PIC-Kit4 that we'll be using in the labs, so you need to install these. As we've downloaded the XC8 compiler ourselves, you can uncheck this box at the end asking you to download it. Now let's install the XC8 compiler. Now, we're only using a free license, so you can just leave free checked. Again, I need to stress that you should use the C drive for your installs. And you also want to add the XC8 compiler to the path. That's everything for the XC8. When you boot MPLAB for the first time, you'll be greeted with this splash screen. I find it's useful to disable this, so to stop cluttering your interface. You can also close these two windows. I also find that the toolbar comes quite cluttered in MPLAB, which especially this can make it quite difficult if you have small monitors on things like laptops. So some things I'd recommend that you remove by right-clicking on the toolbar is the How Do I section and also the MPLAB Tools section. This just gives you a bit of a cleaner interface for working. I go through how to create a project in the handbook in detail, but here if you just want to create one quickly, select File, New Project. It's an application project for assembly. The device we're using is a PIC-18F8722, so enter that here. And to start with, we'll use the simulator and not the PIC-Kit4. If you had your PIC-Kit4 connected over USB, you'd see that there. And we're using the PIC-AS assembler, so you need to select that here. Here you can give your project a name, and I know I've said it quite a few times, but please make sure this is on your C drive. You might have issues if you have it on different drives, or if you've got international characters. And that is everything for creating a project. Without a source file, we've got nothing we can build, so we need to create an assembly source file. To do this, you right-click on the source files section and say New, and then select Other. And you want to select assembler, and the extension we use is .s. Here you can just give the file a name. I give it the name example, but feel free to choose whatever you want. Okay, and then here we can see our first source file open on the right in the editor window. So now that we've created our project, let's see how we can configure it. First of all, on the bottom left, if you look here, this is where you can see all the project information. You can see information like the device we're using, the compiler number, so here we're using the PIC-AS assembler, also the debug tool. So here you can see it's using the simulator right now, but if we were using the PIC-Kit 4, you would see it here. If you want to use it, you can plug it in over USB and restart MPLAB, and you can choose it. If you want to change any of these options, you can click the spanner icon here, and then you can change things like the debug tool that we're using. So you would see the PIC-Kit here if you plugged it in over USB. You can also change the device, so if you won't for this course, but if you wanted to program a different PIC, you could do here. You can change the debug options, so for the simulator there's some options there, as well as you can pass some arguments to the PIC assembler. I'll go into these in a moment. Also, if you click this icon, you can pull up the PDF of the datasheet of the device. So for us, it's the PIC-18F8722, but depending on your project, this might be a different device. We'll come back to that in a second. Another useful option to set is to have the device pause on the first line of code, which is called the reset vector. So if you go to Tools and Options and to Embedded, you can see there's an option for on startup, you can halt at the reset vector. So if you change that, when you go into debugging mode, instead of just running through the code all the way to the end and get to the end, it'll stop on the first line of code. Okay, let's add some code to the project. Now, before we begin, I just want to make you aware that I've created a project for you on GitHub, which you can either download as a zip as a whole project and then open inside MPLAB, or as I'm going to do now, you can just copy the source code directly from this project and paste it into the file that we just created, as so. Okay, so I know this code can look quite scary to a beginner, and trust me, everybody in the class will be feeling the same way looking at this. So before I begin to give you an overview of it, I'd just like to go through a few caveats. Caveat number 1 is you can get much more material out of the handbook. So this tutorial is just designed to be a gentle introduction to MPLAB and how to use its debug and upload code. It's not to really go through the source code, although I am going to try and do it a little bit for you. So yeah, if you need help, go to the handbook first. Number 2 is if you're not sure about any of these keywords, then there's a guide provided by Microchip, which is called the PIC-AS Assembly User Guide. So if you just search this on Google, you'll be able to find every one of the keywords that are referenced, and as well as that, the linker options, which I'll be getting into in a moment. And then the third caveat is that you don't really need to understand all of this for the exam or to pass this course. Really, this code at the top, everything above start, will just be boilerplate, and you can just copy and paste it into all your examples. And your main task going forward will be to add the instructions in the start section, as well as come up with some loops of your own. So what are we looking at here? Well, the first thing to be aware of is that this is not just executable code that's going to be run by the processor. We're also looking at assembly directives, which are information that we're just passing to the assembler to tell it things like where should our code be stored, or whether we need to configure the processor in a specific way. So everything that you can see outside of the labels, so things like the psets, the includes, the configs, the radix, the processor, these are all assembly directives, and we're just passing this information to the assembler. Everything inside the labels is code that's going to be executed by the processor. So taking this line by line, the first line is just telling the assembler which processor we're going to be using. So you can just see we've specified it to be 18F8722. So this just lets the assembler know which instruction set we're using. The second line is just setting the radix to be decimal. So by default, it's decimal. So this line is actually redundant, but it's good to practice to include it so other programmers know quickly that you're using decimals by default. This could also be hex or oct if we're using octal numbers. So if, say, for example, we had hex there, the number move literal 22 on line 20 that you see, that would be the hexadecimal number 22 and not the decimal number 22. There are two different values. The next lines are called config bits, and the process is quite complicated and it has quite a few different modes that it can run on. So, for example, it can have different oscillators, time instructions, or it can run at different voltage levels. So these bits here are us telling the processor, first of all, that we want to use the crystal on the PCB. So that's called the high-speed external crystal, HS. Second, we don't want to use the watchdog timer. For those that don't know, a watchdog timer is a safety feature that is included on some processors. It's just there to check whether the processor is locked up or not. So if, for example, the processor are locked up for a few milliseconds, the watchdog timer can come along, notice that it's been locked up, and then reset the whole processor. We don't need that feature, so we've turned it off there. And then the last option, the low voltage programming, that is an option that some PICs have where they can be programmed down to lower voltages than the 3.3 and 5 volts that we're using. We don't need it, so we're just going to turn that off. This isn't the only configuration bits that are available to you. So if you'd like to view all of them, you can just go to Window, Target Memory Views, and Configuration Bits, and that'll bring up this menu here. And here you can see all of the different options. So for the oscillator, it's not just high-speed external, there's actually quite a few different ones, and everything else is on there. You can also click this button, Generate Source Code to Output, and then that will just generate the source code so you can copy and paste this directly into your code. For this course, though, you never need to change those configuration bits. They can stay exactly as they are right now. But for the future, maybe you've got some projects where you want to change the oscillator, or maybe running low power modes. That's where you'll be doing that kind of thing. This next file, xc.inc, is not essential to include, but it does save you some time because it has all of the definitions of where special function registers live inside of the specific device's memory. So we'll get into it soon, but for things like the GPIO configuration registers, say, for example, LATF or TRISF, this file tells the assembler where those specific memory locations are on our device, so the PIC-18F8722. You can open it from within MPLAB, and I've put the path on the screen right now, but for your projects, it's just useful to include. The next thing you might notice is that the program has been split up into two different sections, or PSECs as they're called, program sections. We have one at the top here called Reset Vector, and one at the bottom that I've named Start. In the Reset section, we just have a single line of code telling the program to go to Start, whereas in the Start section, we've got the main body of our code. So what are PSECs, or program sections? Well, in PIC assembly, all code and data must be split up into its own section. The reason you do this is that you might not want to store all of your program in one contiguous block of memory. You might want to, for example, have different teams within a company having their code stored in different sections of memory. If you think about the program memory as a big ring binder, then the program sections are the dividers, and the code or data is the pages between the dividers. Some instructions you might want to force into specific locations in memory. For example, the reset vector must be stored at the first location that the PIC boots to. Whereas other code, you might not care where it's stored. You might just want to leave it up to the assembler to figure out where to put it. The class identifier is MPLAB's way of classifying what is to follow inside the program section. So, for example, it could be code that's inside the section. It could be data that needs to be stored in RAM, data that needs to be stored in ROM. There's a few different options available to you. All it is doing is just telling the assembler where to store the program section in memory, or how it should be allocated in memory. We've used the code class, so the assembler knows that this needs to be stored inside of program memory. Next, the relock flag is something we'll be getting to later in the course when we talk about instruction sets, but all the number 2 is saying here is that the device we're using the instructions are 2 bytes long. The reason we specify this is to avoid the assembler from storing our program sections on odd numbers. If our instructions are 2 bytes long, then we don't want to overwrite some of them by choosing an odd value of memory location to store our section in. And finally, you have the instructions, which is where you'll be living for most of this course, and most of the activities will be around putting the instructions in this section. There's one last thing we need to do before we can build this code, and that is to link the PIC-AS to the memory locations that we want them to be stored in. So right now, MPLAB doesn't know where reset vector wants to be stored, but we know that it needs to go in the location of the reset vector, wherever that is. So pulling up the datasheet, if you search for reset vector, you'll find it mentions here that the reset vector is address 0, 0. That's quite logical. And here's a diagram just showing you how the memory is located. That means that if we want this instruction, this goToStart, to be the first thing that's booted when the PIC loads, we need to put an argument in to the linker to let it know to place that instruction at 0. Here in the global options, you can see where I've placed that argument. Now, this line can look quite confusing to a beginner, and don't worry, you don't really need to ever change this. But just to go through it, WL means passing an argument to the linker, -P means place, and then after that, it's just the name of the PSEC. So you can see I've got place, something called reset vector, at address 0 in hexadecimal. I've then arbitrarily chose to place start at address 200 in hexadecimal. I could have placed this at any other address though. Could have been 3000, or address 1, or address 201. I just want to show you as an example that you can choose to place your PSECs anywhere you want. Okay, we're finally at the point where we can build the code. To do so, just click this clean and build icon up here, and you should see it go through the build process. And hopefully you should see successful. And to begin debugging, just press this button here, and that'll launch the debugger. We're currently using the simulator. And as you can see here, it's stopped on the first line as we asked it to stop at the reset vector. And you can also see, look, the program counter here is 0 because that's where we told it to store. These buttons here allow you to step through your code line by line. So we're currently at address 0, but if I press this button, we've jumped to start, and you can now see, look, the program counter's changed to 200 because that's where we told the PSEC to be stored. This code just takes the value 22 and stores it in memory location 10. It then takes a binary value and stores it in memory location 11, and then a hexadecimal value and stores it in memory location 12. And then finally just gets caught in an endless loop here. If you want to see these memory locations change in real time while you debug, you can go to Window, Target Memory Views, and then File Registers. This brings up the whole map of the memory, which you can view either in hex or in binary, decimal, and characters. So right now we move 22 to the working register, and if we move it to address 10, you should see there live, look, the value of 22. Now we've put this binary value in the working register, but wouldn't it be nice if we could actually see the working register change in real time? Well, we can do that. We can create a watch like this, and you could just type here wreg, which will bring up the working register. And you can see the previous value of 16's there, which is 22, but in hexadecimal. You can change this so you could view the values in binary or decimal or hexadecimal. And if you look here, you can see 22. So we're expecting that value. If I press now to change to the next line, we should see there it's changed. And the binary value is in there, and also the representation in decimals right next to it. And we're expecting to move that number, which is 41 in decimal, to address number 11. So we'll bring up the file registers again, and we should see B here, which is 11, change. And we do, 41. And then lastly, we're going to put 15 in the working register in hexadecimal, which is the number 21 in decimal. And last line, we're just going to put that into address number 12. And then finally, it's just going to get caught in this endless loop. The watch windows also give you access to all of the other special function registers on the PIC. So, for example, if you're configuring the GPIOs later in the course, you might want to have a look at LATF or TRIS-A, for example, or there's a lot of different configuration registers. But you can see the values of these live. Another nice feature is that you can see the program memory. So if you just go to target memory views and then program memory, you can see here all of the instructions line by line in each memory location. So here in 00, the reset vector, you can see that go-to line. Whereas here it says go to OX200, whereas we've got go to start. But that kind of tells you that the labels are just memory locations, representations of memory locations. If I browse to address 200, then we should see all of our code from our main loop. And here you can see it. So move literal 22, you can see that it's actually been represented to the processor as OX16 and 10 is OXA, but it's the exact same code. You can reset by pressing this button. You can set breakpoints. So if I now press play, the code will run until it gets to that breakpoint. You can set 2 different breakpoints at the same time. So now I can press play again and the code will go all the way until that next breakpoint. You can reset as many times as you want. So I'm resetting again now, pressing play. You can stop debugging by pressing this button. And then you can debug as many times as you want. Just make sure you build each time before you debug. You can view the special function registers as well live. So if you don't want to make watch windows, you can just scroll through and see them all live like this. And that is every debugging feature that you will need for this course, as well as a quick overview of how the software works. That concludes this video, and I look forward to seeing you in the labs. Thanks.